so determine if the function is 1 to 1 using derivatives. Let's take the derivative of the function. I understand that the square root of x minus 2 is the same thing as x minus 2 raised to the 1/2. So in taking that derivative, using a chain rule, I bring down the 1/2. Got that quantity of x minus 2. New power, if I subtract 1 away from that original 1/2, is going to be negative 1/2. And then to complete the chain, you tack on the derivative of that x minus 2, which is 1. That's the derivative of the original function. Since we have a further application for it, let's simplify that. I notice with the derivative I've got this product that involves a fraction, involves a quantity to a negative exponent. So that means as I simplify this, I've got to set up a great big fraction. In that fraction, I know there's going to be a denominator of 2. I know that because of this fraction right here, 1/2. I also know there's going to be a quantity of x minus 2 raised to a positive power of 1/2 because of this negative exponent on that quantity there. As far as what's left on top, well, what is left on top? Just 1, because you have a 1 here, you have a 1 here, multiply that out. There's the simplified form. All right, here's what we're going to do with this derivative to help us determine if this function is 1 to 1. We're going to find some values that are known as critical numbers. I'm going to get into further detail later on as to what critical numbers are specifically, but right now we're just going to kind of use this process to help us out. So to find a critical number, you do two things. You look to see where the derivative equals 0. You also look to see where the derivative does not exist. Now here's the thing about a rational function, at least in this derivative form. If you're trying to see that that derivative equals 0 and it's a rational function, the only way this can equal 0 is if the numerator equals 0. That's the only way that's possible. So if I take my numerator expression of 1, I set that equal to 0, and I try to solve for something, there's nothing there to solve for. Right? 1 does not equal 0. Therefore, does the derivative ever equal 0? Okay. Derivative never equals 0. We can't get a solution from that side. That's okay, it happens. Now on the does not exist side, for a derivative not to exist, well that means, in the form I have right here, if I was dividing by 0, there'd be an issue. So, this part down here, we don't want that to be 0. Right, that can't be 0. Now, in solving for x, though, what would make that equal 0? X is 2, right? So when x is 2, that would make the derivative not exist. This x equals 2, this solution I got back from this side, is what we will eventually be calling this critical number and have a further definition for. Right now, it's just a value we're using to see if the function is 1 to 1. And to finish off this problem, what we're going to do now is set up a little 1-2 chart to organize some information. In that 1-2 chart, we're going to have 2 columns, one devoted to the x values, all x values, and one devoted to the derivative itself. Right? If we're going to use the derivative to determine if the function is 1 to 1, this column has to revolve around the derivative. As we set this up on the x side, since we're covering all values of x, we're going to start at negative infinity. And we're going to work our way up to this critical number we found of 2. We're going to pause at 2. And we're going to recognize that the derivative of the function at 2 did not exist. Right? That's how we found this answer in the first place. Derivative did not exist. Then we're going to set up an interval after that. Since we're covering all x values, we're going to go from 2 to infinity. We set up our intervals. We focus in on these intervals by selecting values from each of those intervals and plugging back in to the derivative. So for this first interval here, I'm looking at values that are less than 2. So something less than 2 would be easy to work with, 0, right? If I take 0 and I plug into the derivative, so I'm plugging in right here, all I need to make note of is what kind of answer I get back. If I take 0 and I plug in over here, get 0 minus 2 is negative 2. This 1/2 means you're taking the square root, right? Can you take the square root of negative 2? Not without going to imaginary land, right? That's not going to work. So since that's not going to work, I'm not going to get an answer back, and I can assume that's true for the rest of the values on that interval. As for this interval down here, selecting something that's greater than 2, say 10, if I plug in 10, you got 10 minus 2, 8, you're taking the square root of 8. Okay, I didn't pick a great value there, though, but it is positive, right? That's going to be a positive answer multiplied to a positive number, right? Positive number up here. No matter what I plug in for x, this is going to be positive. So what this chart tells us from the results we got back, right, we basically got a couple of results back. When you look at all the signs involved, as long as all the signs are the same throughout, then you have a function that is 1 to 1. So the only signs we got back were down here. So since we got something positive back, what we do is we say, therefore, f is 1 to 1. And as we do with therefore statements, we say why this is true. So because, well, our reason is the derivative, since it's positive, it's greater than 0 for all values of x. And really, when you set up a chart of this type, you don't have to include this interval. And you would know that if you go back to the original function and look at its domain. All right, if you look at the domain on the original function, x minus 2 is greater than or equal to 0, so x has to be greater than or equal to 2. We know that rules this guy out. So if you have it in the chart, that's okay. You just find that it does not exist because it didn't work for the domain in the first place. But if you exclude it from the chart because you know something about the domain, that's even better, right? You can just include this part down here, analyze the sign you're getting back for the derivative. Whatever that sign is, that sign's telling you right here why this function is 1 to 1. All right, we got a parabola. We know it's not going to be 1 to 1, but we're trying to show why. So we take the derivative. As you take the derivative of this, pretty straightforward. It's going to be 2x. We use this critical numbers approach, where the derivative equals 0, or the derivative does not exist. Here's the thing about the derivative we found is 2x. If we're looking at this derivative being equal to 0, then take 2x, your derivative set equal to 0, solve for x. X is 0. Pretty easy. But the does not exist side we can take out because, long story short, this is not a fraction. We're not dividing by something that has an x in it. So there's no denominator to consider. We got the one critical number here to work with. That critical number is 0. So I set up my 1-2 chart off of that. Columns consist of an x column and a derivative column. On the x side of things, we're covering all the x's here. So we start at negative infinity. We work our way up to 0, our critical number that we found. We pause at 0, and we appreciate at 0 that the value of the derivative is 0, right? Because that's how we found 0 over here in the first place. And then we continue on from 0 to infinity to cover the rest of the x's. Okay, it's now number picking time. We pick numbers on each of these intervals. We plug into the derivative. So right here, and we see what kind of answers we get back. Take any number that is less than 0, so a negative number, plug in over here. What kind of answer do you get back? Negative. It's a positive times a negative, it's negative. For the positive side, any positive number goes in here, we get a positive result, right? So for all the signs that you get back, if those signs are the same, this is a one-to-one function. If they're different, it's not. So obviously these are different. We slap our therefore on there. We say therefore f is not one-to-one. And we say why. The reason why is because, well, f prime of x was greater than 0 for the positive stuff, or f prime of x was less than 0 for the negative stuff for all of our x values.